The next topic is periodic solution of one-dimensional wave equation in cylindrical coordinate system. Here we are considering cylindrical coordinate system. Okay. First let us see what is periodic solution. Periodic solution is actually a solution that periodically depends on independent variable. Okay, so if I write dou square u by dou t square, here obviously t is our independent variable, u is dependent on t, so u is dependent variable and t is independent variable. Okay, so if I write one graph like this is t, this is theta, 0.2, 0.4, 0.6, 2, 3, 4. Okay, here you can see for different values of t, you have different theta values. You can observe that, isn't it? So when let's assume this is a 0.08, for when t is equal to 0.08, your theta value is almost 4.3 or 4.2. When t is 0.2, your theta value is 4.2. Okay, you can observe that. This is nothing but your periodic solution for some equation. I have just considered one random graph to explain periodic solution. Okay, this graph will be the solution for some equation. This is what actually happened in your wave equation as well. Here we are considering cylindrical coordinate system. So we have standard equation for cylindrical coordinate system. If I write dou square u by dou t square is equal to c square into dou square u by dou x square. This is for xy plane, isn't it? Now we are moving to cylindrical coordinate system. For cylindrical coordinate system, the equation is 1 over c square into dou square u by dou t square is equal to 1 over r into dou by dou r of r into dou u by dou r. This is the standard equation in the case of cylindrical coordinate system. This part remains the same. Since we were using xy plane, this was dou square u by dou x square. In cylindrical coordinate system for one dimensional, we are using only r. Okay, for that this will be the right hand side. Now what I will do is I will rewrite 1 over r as it is. What I have to do, I have to differentiate r and dou u by dou r with respect to r. Okay, let's differentiate that. Since it is a partial differential equation, first I will treat r as constant. You can use product rule of differentiation. Keep r as it is. If you differentiate dou u by dou r with respect to dou r, with respect to r, you will get dou square u by dou r square plus dou u by dou r as it is. If you differentiate r with respect to r, you will get 1. Isn't it? So this will be equal to 1 over r into dou square u by dou r square plus dou u by dou r. I will write this as dou square u by dou r square plus 1 over r into dou u by dou r. I have just multiplied this 1 over r to inside my brackets, inside terms. So r gets cancelled. You will get dou square u by dou r square. If you multiply this, it will be 1 over r into dou u by dou r. I will call this as equation number 1. Okay. So initially while doing separation of variables method, we assumed our solution will be in the form of u of x comma t is equal to x of x into y of y. In the case of inhomogeneous solution, we assumed u of x comma t is equal to u of x plus v of x comma t. So in the case of periodic solution, our solution will be in the form of u of r comma t is equal to f of r into e power I omega t. I will call this as equation number 2. Okay. Since it is a periodic, omega will exist. You know that omega is nothing but angular frequency. Okay, so now let's continue this. In my equation 1, I have dou square u by dou t square and dou square u by dou r square as well as dou u by dou r. So I should differentiate this equation with respect to t twice so that I can substitute here. With respect to r once, I can substitute here. If you differentiate with respect to r twice, you can substitute here. Let's do that now. So this will be a periodic solution of your equation 1. If you differentiate with respect to t, you will get f of r as it is I omega into e power I omega t. If you differentiate again, you will get utt is equal to f of r as it is I omega whole square into e power I omega t. I square is nothing but minus, so it will be minus f of r into omega square e power I omega t. This is nothing but your utt. I will call this as equation number 3. Now I have to differentiate with respect to r once. I will substitute here. If I differentiate with respect to r twice, so that I can substitute here. So ur is equal to f dash of r. This is with respect to t. I will consider as constant. So urr will be f double dash of r into e power I omega t. Call this as equation number 4. This as equation number 5. Now substitute 3, 4, 5 in your equation number 1. So you will get 1 over c square into minus f of r into omega square e power I omega t is equal to f double dash of r e power I omega t plus 1 over r into f dash of r into e power I omega t. Since you have e power I omega t in all the terms, divide e power I omega t. Okay, from both sides of your equation you can divide e power I omega t, or else you can take that out in both the side and you can do cancellation rule also. So what you will get if you divide both sides by e power I omega t, it will be minus f of r omega square by c square is equal to f double dash of r plus f dash of r by r. Okay, I will write this equation as f double dash of r plus 1 over r into f dash of r plus omega square by c square into f of r, which is equal to 0. I will call this equation as equation number 6. Okay, this equation is actually called as Bessel's differential equation. Bessel's differential equation of order 0. Okay, of order 0. This equation, I repeat, your equation 6 is called as, this is a standard equation. This equation is called as Bessel's differential equation of order 0. Okay. And the solution for this equation is given by f of r is equal to a into j naught of omega r by c plus b into y naught of omega r by c. This is a standard equation. If you solve this equation, you will get the solution. You need not to solve this equation. You can just write the solution. Okay, I repeat. This equation number 6 is in the form of Bessel differential equation. In your ODE class, you have seen that Bessel differential equation is x square y double dash plus x y dash plus x square minus n square into y is equal to 0. This is your standard Bessel equation. You have solved this equation in your ordinary differential equations in the part of power series. Why it is order 0 is because if you compare these two equations, you can write this equation in this form. Like if I divide the whole equation with x square, I will get y double dash plus 1 over x y dash plus x square minus n square by x square into y is equal to 0. So you can compare these two equations now. But in the last term, that is in the third term, you have omega square by c square. If you split this, you will get x square by x square minus n square by x square. Observe carefully now. This term is not there, isn't it? That means n is 0. If n is 0, you will call Bessel differential equation of order 0. Okay. Now, if you solve this equation, you will get this solution. In general, I have written the solution. This is our solution. We actually write in the place of j naught, jn, and in the place of y naught, yn. Since order is 0, I have written j naught and y naught. Okay. Now, in this equation, j naught and y naught are Bessel's function of j naught is Bessel function of first kind and y naught is Bessel function of second kind. So, in the case of first kind, you will get a solution as Jn of x in general I am writing. This will be equal to summation r is equal to 0 to infinity minus 1 power r 1 over r factorial into gamma of n plus r plus 1 into x by 2 power 2r plus n. This will be the solution of Jn of x in first kind. Okay. This all this concept will come under special function. If you check in advanced differential equation textbook, you will get the solution. How you will get everything, you can see there. It's a solved solution. Okay. In the case of second kind, y naught value will be or yn value will be equal to limit v tends to n j v of x into cos v pi minus j minus v of x whole divided by sin v pi. Okay. If you compare these two, in the case of x, we have omega r by c. So, now if r tending to 0 means as r tends to 0, you will get solution for this equation. So, don't worry about this. In this equation, what will happen? If it is, if v tending to n means, it will become sin n pi. For different values of n, sin pi will be 0. Anything divided by 0 is infinity. So, I will write this as r tending to 0, your y naught of omega r by c tending to minus infinity. Okay. So what we will do is we will choose b as 0. Choose b is equal to 0. So if you choose b is equal to 0, your solution will be f of r is equal to a j naught of omega r by c. This is your equation number 7. Okay. Now substitute your equation number 7 in equation number 2 for f of r. So the final solution will be u of r comma t is equal to a into j naught omega r by c into e power I omega t. So this will be the periodic solution of your one-dimensional wave equation in cylindrical coordinate system. Now let's move to spherical coordinate system. There is a small change in considering the standard equation in the case of spherical coordinate system, that is 1 over c square into dou square u by dou t square is as it is. Here it is 1 over r square into dou by dou r of r square into dou u by dou r. So similarly what I will do, I will retain 1 over r square as it is. If you differentiate these two terms with respect to r, you will get r square into dou square u by dou r square plus 2r. If you differentiate r square with respect to r, you will get 2r into dou u by dou r. This dou u by dou r is as it is. Okay. Multiply 1 over r square to inside, you will get dou square u by dou r square plus 2 by r into dou u by dou r. This is nothing but 1 over c square into dou square u by dou t square. I will call this as equation number 1. Now the periodic solution for this wave equation in spherical coordinate system will be in the form of u of r comma t is equal to f of r into e power I omega t. There is no change in solution form also. So now what you will do, you have to differentiate this equation with respect to t twice and with respect to r twice. So you will get dou u by dou t is equal to f of r I omega e power I omega t. Utt will be minus omega square f of r e power I omega t. Ur will be f dash of r into e power I omega t, and urr will be f double dash of r into e power I omega t. This is 3, 4, 5. Substitute 3, 4, 5 in your equation number 1. So that you will get minus omega square by c square into f of r into e power I omega t is equal to f double dash of r into e power I omega t plus 2 by r into f dash of r into e power I omega t. Now what you will do, since you have e power I omega t in all the terms, divide whole equation with e power I omega t. Divide throughout by e power I omega t. So you will get minus omega square by c square into f of r is equal to f double dash of r plus 2 by r into f dash of r. So I can write this equation as f dash of r plus 2 by r into f dash of r plus omega square by c square into f of r is equal to 0. Again your equation, this is, I will call this equation as equation number 6. Now what we have to do is, since it is a spherical coordinate system, we have to consider one more coordinate system, one more coordinate. Okay. So I will consider f of r as omega r by c whole power minus 1 by 2 into xi of r. This I will call as equation number 7. Okay. Now similarly, what you have to do, you have to find out f double dash of r, f dash of r, and you have to substitute in your equation number 6. Okay, let's find out that f dash of r will be, you have to differentiate with respect to r. So use product rule, you will get, okay, omega by c whole power minus 1 by 2 I will treat as constant. So here what is left out? R power minus 1 by 2 is left out with xi of r. Okay, r power minus 1 by 2 is I will treat that as constant for time being. If you differentiate this with respect to r, you will get xi dash of r plus omega by c whole power minus 1 by 2 is as it is into xi of r into, you have to differentiate this with respect to r. So you will get minus 1 by 2 into r power minus 3 by 2. This is your f dash of r. Now you have to find out f double dash of r. Before that, let's simplify this. You will get omega r by c whole power minus 1 by 2 into xi dash of r minus 1 over 2r. This is 3 by 2. I have taken 1 by 2 outside. So remaining is r power 1 into xi of r. Okay, let's find out f double dash of r now. F double dash of r will be omega r by c whole power minus 1 by 2 into 3 times of 4r square into xi of r minus 1 over r into xi dash of r plus xi double dash of r. It's a normal differentiation, that is you can use product rule to differentiate this. Take this solution and you can differentiate this. Treat omega c power minus 1 by 2 as it is. Differentiate these two. One with respect to treating one as constant and differentiate other. Use product rule. You will get answer for this. Again use product rule for these two and simplify that solution. You will get this. Okay. Now what you have to do? You have to substitute f double dash of r and f dash of r in your equation number 6. If you substitute, you will get omega r by c whole power minus 1 by 2 xi double dash of r minus 1 over r xi dash of r plus 3 by 4 r square xi of r, plus you are just substituting these values here, that's all, nothing else. Here you have substituted. Okay. So after substituting, what I have done is omega r by c whole power minus 1 by 2 is common in these three terms. So I have taken out and I have divided with 0. So you will get 0 itself. So you will get xi double dash of r minus 1 over r xi dash of r plus 3 by 4 r square into xi of r plus 2 by r into xi dash of r minus 1 by 2r into 2 by r is nothing but 2 by 2r square into xi of r plus omega square c square into xi of r is equal to 0. Now simplify further. You will get xi dash of r plus 1 over 4. Take these two and 2 by r minus 1 by r is 1 over r, sorry this is not 4, 1 over r xi dash of r minus xi of r and this xi of r. Okay. First take these two, you will get minus 1 over 4 r square into xi of r plus omega square by c square into xi of r as it is, which is equal to 0. So I will rewrite this as it is. and I will take xi of r common here, plus omega square by c square minus 1 over 4 r square into xi of r, which is equal to 0. Again, if you compare this with your Bessel equation, you will get, you can say that this is of the form of Bessel differential equation. Okay, but this is not of order 0. In the place of n square, you have some value here. Okay, so I will call, since it is, let's take 1 by 4 only, since it is a constant number, 1 over 4, that means n is 1 by 2. So I can say that this is of the this is a Bessel differential equation form with order 1 by 2, and the solution will be of xi of r is equal to a into j. In the place of n, I have to write 1 by 2 omega r by c plus b into y power 1 by 2 into omega r by c. J half and y half are Bessel function of first kind and second kind respectively. So we know that for first kind there is a solution. For second kind, if you consider r is tending to 0, this whole term will tends to minus infinity. As r tends to 0, you will get y half of omega r by c is tending to minus infinity. So what you will do, you will choose b is equal to 0. So the final solution will be xi of r is equal to a into j half of omega r by c. Now what you have to do, you have to substitute this value in your equation number 7. In the place of xi of r, you have to substitute. So what you will get, f of r will be equal to omega r by c power minus 1 by 2 into a into j half into omega r by c. Is this your final solution? No, you have to substitute f of r in your equation number 2. Okay, you will get u of r comma t is equal to omega r by c whole power minus 1 by 2 a into j half of omega r by c into e power I omega t. This will be your final solution of spherical coordinate system for one-dimensional wave equation.